Good morning to all of you.
Good morning, sir.
Morning, sir.
Good morning. Is my screen visible?
Yes, sir.
Okay. So are there any questions, doubts? Okay, so if there are no questions, let me start. So we are continuing with the dynamics. So for few, I will demonstrate for few more elements how to get the mass matrix. Although I think I have explained you sufficiently enough to formulate the dynamic equations of motion for any element. But let me take a few more examples. So we are continuing with the dynamics. Yeah, is the screen visible? In between, I had to close it. Yes. Okay. So we are continuing with dynamics. So I have in the last class I talked about the mass matrix for truss element and the Euler-Bernoulli beam element. So today let me also give the mass matrix for Timosenko beam element. So now in the Timosenko beam element, in the Euler-Bernoulli beam element, main assumption is that normal to the middle surface remains normal and straight after deformation. And in the Timosenko beam element, it is not necessary that it is normal. So let us say this is the element. The coordinate system is this is x and y. Length of the element is this is node 1, this is node 2, and when it deforms, so in the deformed condition, this is the center, this is the deformed center line. If we take any line, so it rotates, so now that line becomes this. So this displacement, if you take, this is y into theta. Now the normal is not necessarily normal to the deformed middle surface. So in this case, if you see displacements, so now if you look at the displacement along x, which is a function of x, y and t, so this is minus y into theta. Theta is a function of x and t. And second displacement along y direction is a function of only x and t. So v is a function of only x and t. So similar, so this is what you need, of course, for the stiffness matrix. You need to write the normal strain epsilon xx and the shear strain gamma xy, and then from there you can get to the strain energy and the stiffness matrix. So I am only now looking at the mass matrix. So just look at the velocities. So if you look at the velocities for this, velocity along u will be u dot, which will be equal to minus y into theta dot, which is a function of x and t. The other velocity component would be v dot. So if you look at the kinetic energy, so kinetic energy T is half of integration along length, integration over cross-sectional area of the element into rho, and then we have u dot square plus v dot square dA dx. So yeah, now this is the general expression we have. Once we know this velocity, and then what are the assumptions in the element, you can write the uh, basically the final expression for the kinetic energy. So from this we will get T equal to half integration 0 to L integration over cross sectional area rho, and U dot is minus y into theta dot, so its square would become y square into theta dot square, and V dot is as it is V dot dA dx. Now if you do the cross sectional integration, so you can see that T can be written as half integration 0 to L, and integral rho y square dA would be equal to rho into Izz. So the first term would be rho into Izz theta dot square, and second term is integral rho dA will be equal to rho A. So rho A into A V dot square and dx. So this is what we will have. Now, so this you can write in the matrix form, product of matrices and vectors. So integral 0 to L, and then you can put here V dot theta dot transpose, and in between this matrix, so say rho A0 rho into Izz. So the same expression you will get V dot theta dot dx. So you can write actually the expression for kinetic energy in this form for this case. And so and if you multiply these matrices and vectors, you will basically will get this expression. So we have just same thing, we have rewritten it. Now for the two-noded Timasenko beam element, V and theta are approximated using linear interpolation functions. So V and theta would be equal to, V will be N1 V1 plus N2 V2. So it would be N1 0 N2 0, and theta would be 0 N1 0 N2, and into the no elemental degrees of freedom, V1 theta 1 V2 and theta 2. So here N1 is 1 minus x by L, and N2 is x by L for the Timasenko two-noded Timasenko beam element. So you can say that V and theta can be written as H into dE. This is H and this is your dE. So now we need actually velocity. So you can differentiate this with respect to time. So we will get V dot theta dot will be equal to H is only function of x, dE is a function of time. So we will get here dE dot. So now if you look at now the expression for kinetic energy, T will be half integration 0 to L, and then V dot theta dot transpose would be dE dot transpose into H transpose, and then B in between we have this matrix. So we have rho into a 0 rho into Izz, and then into again H matrix into dE dot dx. So this is what you have, and now we can write this because no dE dot can be taken out of the integration sign. So we can write this T as half of dE dot transpose into element level mass matrix ME into dE dot, and where this mass matrix is where element level mass matrix ME is, and you will note here that in the Euler-Bernoulli beam element, because it is thin, so we have neglected this rotary inertia term rho into Izz. But no, now we are talking of Timasenko beam element, so it is relatively thick, because Euler-Bernoulli beam theory would be applicable to very thin beams, and this will be for relatively thick beams. So this term is also considered here. So we are not neglecting that. So where the element level mass matrix CME is integration 0 to L and H transpose rho A 0 0 rho into Izz into H dx. So this is the element level mass matrix. And now if you want to get to the final expression, so you can say that this ME element level mass matrix is integration 0 to L, and then your H transpose is N1 0 0 N1 transpose we are taking N2 0 0 N2 rho A 0 0 rho into IZZ, and then this is N1 0 N2 0 0 N1 0 N2 dx. So if you multiply all of these, so you will see that you will get this ME mass matrix as integration 0 to L, and this is going to be 4 by 4 matrix, and the elements would be this row A N1 square 0 row A N1 N2 and again 0, and then here 0 rho into IZZ N1 square 0 rho into IZZ N1 into N2, and then this will be rho A N1 N2 0 rho A N2 square 0, and then 0 rho into IZZ N1 N2 0 rho into IZZ N2 square. So this is what you will get. And so now if you integrate this, so B will get the mass matrix for the Timosenko beam element. So you will get this CME as, and this we are deriving from the, as you see, from the shape function. So it's a consistent mass matrix what we are talking about. So this integral would be rho AL by 3, rho A N1 square integral would be rho AL by 3 0. This would be rho AL by 6 0, and then we have 0 rho IZZ L by 3 0 rho IZZ L by 6, then we have rho AL by 6 0 rho AL by 3 0, and then we have 0 rho IZZ L by 6 0 rho into IZZ L by 3. So this is what you get as a mass matrix. So this is obviously consistent mass matrix. And now if you want to get the, want to write the lumped mass matrix, so one way is that we lump the mass at the two nodes and also the inertia, rotary inertia. So lumped mass matrix would be again say denoted by ME. So that would be simply rho AL by 2 0 0 0 and rho IZZ L by 2 0 0 0 0 rho AL by 2 0, and then we will have 0 0 0 rho IZZ L by 2. So this will be the lumped mass matrix. So this is how now you get the mass matrix for the Timosenko beam element. So of course for the lumped mass matrix you don't have to matrix. So now let's say two more elements I want to discuss and then go ahead further. So now if suppose similarly you have the plane stress and plane strain element. So and of course the equation of element level equation of motion would be ME into D double dot plus KD is equal to F external plus F internal. So that form is same. So you have to of course get the stiffness matrix for the element and use it for solving dynamics problems involving Timosenko beam element. Then same way now if you look at the mass matrix for plane stress, mass matrix for plane stress, plane strain element. So now again the form of kinetic energy is T half integration over volume rho into the two non-zero components of velocities are u dot and v dot. So u dot square plus v dot square into dv, and this volume integral can be split into the integration along the thickness and area. So integration over area, integration over thickness, minus h by 2 to plus h by 2 into rho into u dot square plus v dot square dA, dz dA. So now because u dot and v dot are assumed to be for the plane stress plane strain element constant through the thickness, so the thickness integration simply gives you h. So this will be half integration over area, and then we will have rho h and u dot square plus v dot square dA. So this is this can be written as T equal to half integration over area. Then we have this rho h remains as it is. Then we have u dot v dot transpose into u dot v dot dA. So this will this product will give you ultimately the same expression. But since we have UV in terms of matrix and vector product, so we want to write in this form. Now we are talking of, say, suppose if you take you can take either a triangular element, or you can take a quadrilateral element, 4-noded quadrilateral, 8-noded quadrilateral. So you can have different elements, and you can develop the element level mass matrix for that. You starting from this T, what we have got, half of integration over a rho h u dot v dot transpose into u dot v dot dA. So from this you can develop. So as an example, let me take a 4-noded isoparametric element. So we have element in the physical coordinate space xy, arbitrary quadrilateral, and these are the nodes. And this is mapped to I square in the natural coordinate space. So we'll have xi and eta. Nodes are 1, 2, 3, and 4. So, and each node, the degrees of freedom are u1, v1, u2, v2, and so on. So these are the degrees of freedom. So you will be able to write the interpolation for u and v is equal to, again, n1 0, n2 0, n3 0, n4 0, and then 0 n1, 0 n2, 0 n3, 0 n4 into the elemental degrees of freedom. So that is u1 v1, u2 v2, u3 v3, u4 v4. So this obviously you can write it as h into dE, and the same function in terms of xi and eta for a 4-noded isoparametric element you already know. So so from this you can write your u dot and v dot as basically h into d dot. And once you have this, then you can write the expression for kinetic energy. So if you look at the kinetic energy, P is half. Now integration over area, we have rho h, and then we have this d dot transpose into h transpose into h into dE dot and dA. So this is what you can write, and so we can say that this T we want to write half, and d dot transpose into ME into dE. So these are the actually the standard steps, but I just want to demonstrate it for different elements. So the element level mass matrix over here, element level mass matrix ME is equal to integration over area rho H transpose into H dA. So this can be written as, because we are dealing with the natural coordinates, so area integral can be split into double integral -1 to +1 -1 to +1 rho into H capital H transpose into H into determinant of J into d psi d eta. And this you can write finally using Gauss quadrature numerical integration. So now finally you can say this mass matrix for the plane stress plane strain element would be summation I equal to 1 to n, j equal to 1 to m, and then we have rho H into H transpose into H into determinant of J. This is evaluated at xi I eta j into wi wj. So using the Gauss quadrature numerical integration scheme, you can write it like this. In this case, you will see we take n and m same, and the highest, because H involves xi and eta for the four noded isoparametric element. So the product H into H transpose would give you xi square and eta square kind of terms. So the highest power of xi or eta is 2. So the m and n would be 2 plus 1 by 2 approximated to next integer. So they will be 2. So that means basically you will use 4 Gauss points in the element to calculate the this mass matrix. So this is xi and eta, one integration point here, one integration point here, one integration point here, one integration point here, and these are the nodes. So yeah, this is how you can write the mass matrix for this. Of course, you will have to evaluate it numerically through the numerical integration. Because the element is arbitrary quadrilateral, so you have to do the numerical integration, because explicit integration will not be possible. So then for one more element, let me also demonstrate you the mass matrix for one plate bending element. Now similarly you can do for others, so I'm just taking one example. So the next is mass matrix. Yeah, so hello, am I audible?
Sir, you are audible.
Yes, sir. Yes, sir.
Okay. Okay. So the mass matrix, so this is standard procedure actually. Now like this, you can develop the mass matrix for any structural element. So mass matrix for a Mendelian plate bending element. So now we have already discussed for the static case. So you already know about what are the assumptions made in this, how the displacement field is approximated within the element. So this is the element, and the coordinate axes are, this is x, this is y, and this is z. And then if we take any normal over here, normal to the middle surface, so after normal it remains straight but not normal. So that is the assumption. So this is the deformed basically normal, and if you look at this, this is z into theta x. So in this case now you already know the displacement approximation through the thickness. So we know the displacements u, which is in general is a function of x, y, z and t. So in this, and we are assuming that there are no in-plane loads, only transversal loads in small deformation. So u and v, u naught and v naught displacements are not there. So this is z into theta x. Theta x is the rotation about positive y-axis, and theta x is assumed to be function of x, y and t. Similarly, v, the displacement at any point along y direction, which is in general a function of x, y, z, is written as z into theta y. Theta y is the rotation about a negative x-axis. So this is also function of x, y, and t. And of course, w is assumed to be function of x, y, and t. The displacement along z direction. U is the displacement along x, v is the displacement along y, and w is the displacement along z. Now, same way, if you look at the velocities, so we differentiate the displacements. So we get u dot is equal to z into theta x dot, and v dot is equal to z into theta y dot, and w dot. So these are the three velocity components. And again, you write the kinetic energy. So the kinetic energy T minus h by integration over volume, and integration over volume is expressed as integration over area and integration through the thickness. So rho and into u dot square plus v dot square plus w dot square, all the three terms are there in this case. So dz dA. So now you can write this as put the expressions for u dot, v dot, and w dot. So you will see that t will be half integration over area, integration over thickness, minus h by 2 to plus h by 2. And then rho, we have u dot as z into theta x dot. So we'll get z square into theta x dot square plus z square into theta y dot square and plus w dot square dz dA. And if you carry out the integration through the thickness, so we will get t is equal to half integration over area, and then we will have this term will give rho h cube by 12. The integration of z square from minus h by 2 to plus h by 2 would be rho h cube by 12 into theta x dot square plus again rho h cube by 12 theta y dot square, and plus this will be rho into h w dot square dA. So this is straightforward. Now you write it, and now this we want to write in the product of matrices and vectors. So you can write half integration over area, and then now you put the w dot theta x dot theta y dot together. So w dot theta x dot theta y dot, and then in between a 3 by 3 matrix. So rho h corresponding to w, 0 rho h cube by 12 corresponding to theta x dot, and 0 0 rho h cube by 12 corresponding to theta y dot into w dot theta x dot theta y dot dA. So yeah, you can write this finally, the kinetic energy of this Mendeleev plate element in this form. So if you multiply all these three, this is transpose here. So yeah, this is transpose, and when you multiply this, you will basically get these terms. So this is no one and the same thing what we have written already. And now let us say again, you can talk of no different elements, but let us take the four noded isoparametric element for Mendeleev plate bending element. So that means we have the element in the physical xy coordinate as the hello हाँ मेरा क्लास है अभी Yeah, so now again, if you take the four noded isoparametric Mendeleev plate element, which is arbitrary quadrilateral in the physical coordinate space and is a square in the natural coordinate space. So we'll have xi and eta. The nodes are 1, 2, 3, and 4. And at each node, the degrees of freedom are w1, theta x1, theta y1, w2, theta x2, theta y2, and so on. So these are the degrees of freedom at each node. So now if you look at the interpolation for w, theta x, and theta y, and then the interpolation for w dot theta x dot and theta y dot. So you know that w, theta x, and theta y will be basically now the degrees of freedom vector, let me write. So the degrees of freedom are W1 theta x1 theta y1, W2 theta x2 theta y2, W3 theta x3 theta y3, W4 theta x4 theta y4. So these are the elemental degrees of freedom. Now W would be N1 W1 plus N2 W2 plus N3 W3 and so on. So will be N1 0 0, N2 0 0, N3 0 0, N4 0 0. And then theta x would be 0, N1 0 0, N2 0 0, N3 0 0, N4 0. And theta y would be 0 0 N1, 0 0 N2, 0 0 N3, 0 0 N4. So you can say that this is H into D, again the same form. So this is H and this is your DE. So therefore you can say that, if you differentiate this, you can write W dot theta x dot theta y dot is equal to H is a function of only xi and eta, D is a function of time, so we will get D dot over here. So now another same thing, you substitute this in the expression for kinetic energy and then you identify your mass matrix. So the mass matrix is element level mass matrix. I am directly writing element level mass matrix for this element, and as I said already that the element level equation of motion format is similar. So the element level mass matrix ME will be integration over area, then we have H transpose into, we have this matrix in between, rho H 0 0, rho H cube by 12 0 0 0, rho H cube by 12 and into H, and then we can write this as determinant into dA, and dA of course then can be split into the integration through the natural coordinate space. So ME is equal to integration from -1 to +1, -1 to +1, and H transpose into this matrix rho H 0 0, rho H cube by 12 0, 0 0, rho H cube by 12 into H into determinant of J into D high into D eta. And then what you can do is you can actually denote this say by CM, so you can write it in the Sartor form. So finally you can say that ME will be equal to you can now you will again evaluate this using Gauss quadrature numerical integration. So you have I equal to 1 to n, J equal to, we will have J equal to 1 to m, and then we will have this whole thing H transpose into rho H 0 0, rho H cube by 12 0 0 0, rho H cube by 12 into H into determinant of J. This whole thing is evaluated at xi I eta j into Wi Wj. So you can use this integration, and as you know in this case also, since we are considering a 4-noded quadrilateral element, so we will take n is equal to m is equal to 2 plus 1 by 2 approximated to next integer, so that is 2. So we will use for again 4 integration points. So these are the integration points. Xi and eta nodes are 1, 2, 3 and 4. So yeah, this is the mass matrix. Now, so this like this, using this you can develop the mass matrix for different different type of elements. Whatever elements we have discussed, for all those elements, you can actually develop the element level mass matrix and therefore the element level equation of motion. So now if I finally in all cases the element level equation of motion is going to be element level equation of motion will be of the form, as we have said already, me into d double dot plus we have this ke into de, that is stiffness matrix, is equal to load vector due to externally applied distributed forces and plus the internal forces at the boundaries of the element. So this is the element level governing equation. And then we have already, through the examples on truss and Euler-Bernoulli beam elements, we have discussed that how to get the finally equation of motion after assembly and imposition of boundary conditions. So we know the equation of motion after assembly and imposition of boundary conditions. So we get this equation we have already said, usually denoted by M as the global mass matrix into d double dot plus we have this k into d is equal to F. So where M is the global mass matrix, k is the global stiffness matrix, F is the global load vector, and d is the global vector of degrees of freedom, and d double dot is the acceleration vector. So now if you talk of this, once you get this equation, then all the techniques which you use for multi-degree of freedom systems in dynamics of vibration course, whatever you learn, all of those are applicable subsequently here. So if you want to look at the free vibrations, say for example, so if we want to carry out the free vibration analysis and particularly the eigen-model analysis, so in that free vibration analysis, we take F to be a null vector, and we assume for the model analysis, we assume that the d, which is a function of time, can be written as d, which is independent of time, into e to the power of I omega n t, where omega n is the natural frequency and I is equal to minus square root of minus 1, and omega n is natural frequency and t is time. So you know when you make use of this assumption, so you can write this equation as now d double dot. So if this is d double dot is going to be minus omega n square into d to the power I omega n t. So you could be able to write this equation as minus omega n square m into d plus k into d, and this whole thing is into e to the power I omega n t is equal to g null vector. So since this should be true for any value of time, so finally then if it has to be true for any value of time, then this term has to be 0, and if you take this term, so you get omega n square into m into d is equal to k into d. So either you can write this as kd is equal to omega n square m into d. So what this is an eigenvalue problem. So through this you do what is known as the modal analysis. So now if we have the eigenvalue problem in this form, we call it as generalized eigenvalue problem. So now for the non-trivial solution, the determinant of the coefficient matrix, that is k minus omega n square m, should be equal to 0, and from that you solve for omega n, the eigenvectors. So now let us say that we have ith eigen. So I am not discussing the methods to solve this eigenvalue problem. There are different methods. From the determinant you can solve. Then the vector iteration. There is a subspace iteration method. There is a Langsaus iteration method. So there are different methods to solve this generalized eigenvalue problem. So I am not, I don't have time to discuss those different eigenvalue extraction techniques, but I just want to discuss actually how to model damping. So one is that if you use the viscoelastic constitutive relation, so from there you will get the dissipation terms automatically, because if you consider the viscoelasticity. But if you want to consider elastic model, then the dissipation has to be empirically incorporated in the equations of motion. So that is what I'm going to discuss, how to get the damping matrix. So let us say when we solve the eigenvalue problem, so we have ith eigenvalue is, let us say, omega ni, and the corresponding eigenvector is, let us say, phi I. So d is equal to phi I. That's what I'm saying. Phi I is nothing but actually di, capital Di. And so similarly, let us say if we have jth eigenvalue is omega nj, and corresponding eigenvector is, let us say, phi j. So then let's look at what is the relation. We normalize the mass matrix, and we normalize the eigenvectors with respect to mass matrix. So then this product so if eigenvectors are normalized with respect to mass matrix, then we will have this phi I transpose into m into phi j. This will be equal to 1 if I equal to j, and this will be equal to 0 if I is not equal to j. So the normalization gives you this is equal to unity, even if the eigenvector is not normalized. So if I and j are different, the product is going to be 0 in any case. But if they are not normalized, the phi I transpose m into phi j will not be equal to unity if I equal to j, but it would be some non-zero value. But if the eigenvectors are normalized with respect to mass matrix, then phi I transpose m into phi j would be equal to unity if I equal to j. Otherwise, it would be equal to 0. So similarly, we will have this phi I transpose into k into phi j. This would be equal to omega ni square if I equal to j, and this will be equal to 0 if I is not equal to j. So this is what you have now. The property of these eigenvectors. So this is known as orthogonality property of the eigenvectors. So that is this is if the I and j are same, that is unity. If I and j are different, then this product is 0. And similarly, if I and j are same, this product is omega ni square. And if they are different, then it is equal to 0. So this is known as the orthogonality property of eigenvectors. Orthogonality property of eigenvectors. So I have not discussed the derivation of this. You can actually derive, this is possible to actually derive this. So that usually we do in the dynamics course. So here I'm not going to do that. So now I know my aim is to introduce to you is the yes.
Sir, whenever we are converting the integration into summation form for mass matrix, so there like we are actually looking at the powers of eta zeta, right?
Right.
For that, okay. And after that, actually, like it happens to come that for Midland plate theory, it is 2 plus 1 by 2. That's why we are taking 2. Suppose if for some theory they have higher power, then we will take like higher power plus 1 by 2.
Higher power. Yes, higher power. Yeah. Suppose the highest power of giant eta is 4. Let's say if you are considering 8 noded quadrilateral element, isoparametric element. Then highest power of xi and eta would be 4. So 4 plus 1 by 2 approximated to next integer, that is 3. So we will then use 3 by 3 integration rule.
And so one more doubt I had was like we always convert from xy to eta zeta coordinates whenever we have a different shaped like element with us.
Yeah.
So why do we like select those kind of shapes at the first place? Why don't we directly start with the rectangular or triangular element kind of
Now
thing?
see, because now in the physical coordinate space, when you look at your geometry, so geometry may not be actually regular geometry. So if it is not a regular geometry, then you won't be able to discretize that into rectangular elements or square elements. But you have to fit arbitrary quadrilaterals. And that is why we want to have an element which can fit into any arbitrary geometry in the physical coordinate space. And that is why the need for a arbitrary quadrilateral element. And whenever there are curved boundaries, so then you actually need curved boundaries of the element in the physical coordinate space. So you will go for 8 noded isoparametric element.
Okay, sir.
So the reason is that in real geometries are not regular geometries. So we need to fit arbitrary quadrilaterals or curved sides of the element into the physical geometry, and that is why we need that kind of elements.
Excuse
So
me, sir.
now, yeah.
Sir, is it possible to assemble two element level equation? One is evaluated in the zeta eta coordinate and one is evaluated in the physical coordinate.
What do you mean by that? No, if you are using isoparametric element, you have to use zeta in the zeta eta coordinates. So the mass matrix is all the interpolation I have already discussed that to satisfy the inter-element compatibility requirements. If you have arbitrary quadrilateral in the physical coordinate space and the formulate the element in that itself, it will not satisfy the inter-element compatibility requirements. So that is why you want to go for the isoparametric element and assume the approximations for the displacement in the natural coordinates so that it satisfies the inter-element compatibility requirement. Okay.
Okay, sir.
But assembly, of course, if you have formulated an element in the physical coordinate itself, you have assumed the variables in terms of the physical coordinates x and y. And if you have the mass matrix, you can assembly is the same. The assembly procedure would be same, whether the element is an isoparametric element formulated in natural coordinate space or the element formulated in physical coordinate space. So the assembly is going to be same. So now I was talking about damping. So if we include damping, then the final equation of motion would be m into d double dot the final equation of motion would be m into d double dot. Now the damping matrix C into d dot plus k into d, no small d, not capital D, that's a small d, is equal to F. So this will be equation of motion. So here, this C is damping matrix. Now how do we get this? So as I said, if you are using viscoelastic constitutive relation, then the damping would be included automatically in that. So you don't have to worry about including the separate damping matrix C. But if you are doing the using elastic constitutive relation, and then there is always inherent damping in the system. So to model that damping, you have to include this damping term. So this C is actually known as damping matrix. Now, how do we model this? How do we get this damping matrix? So now for the elastic model, we cannot get this, but we express it in terms of mass matrix and stiffness matrix. So the popular model is known as Rayleigh proportional damping model. Rayleigh proportional damping model. So in this Rayleigh proportional damping model, what we take is the damping matrix C is equal to alpha is a scalar constant alpha into m plus beta into k. So m and k are this, m is this mass matrix and k is this stiffness matrix that you are getting from your element assembly and imposition of boundary condition. After that, whatever m and k are there, you use here and get this C is equal to alpha m plus beta k. Here m and k are known, but how do we get alpha and beta? So to get the alpha and beta, we depend on the experiment. So we need to know experimental damping factors, and from there we can get these two constants alpha and beta. Alpha is a mass proportional term and beta is the stiffness proportional term. So now if you multiply this whole equation by pre-multiply by phi I transpose and post multiply by phi I, so you can write this as basically phi. So this equation, if I pre-multiply by phi I transpose and post multiplied by phi, so we will get phi I transpose C into phi I is equal to alpha times phi I transpose into m into phi I, plus we will have beta times phi I transpose into k into phi I. So this is what we will get. And now if you look at this phi I transpose C into phi I, this can be written as 2 into zeta I into omega ni, where zeta is the model damping factor for the ith mode and omega ni is the natural frequency of ith mode. And as we know, because if phi I is normalized with respect to mass matrix, phi I transpose m into phi I would be unity, so we will get alpha plus beta, and then phi I transpose into k into phi I would be equal to omega ni square. So you will get this equation in this form, where this is damping factor that is ratio of damping coefficient to critical damping coefficient for ith mode, damping factor for ith mode, and omega ni is the natural frequency, ith natural frequency. So this relationship is very useful to get the basically the alpha and beta. So now what we have to do experimentally, we need to know, if we want to, sometimes we just use either mass proportional damping, so we just have alpha m term, or sometimes we just use stiffness proportional damping, so we will have beta into k in that case. So there you will have only one constant, but if you have both mass and stiffness proportional terms, then you'll have to get these two constants alpha and beta. So to get alpha and beta, we need to know experimentally the damping factor in two modes, say mode 1 and mode 2. So for mode 1, we will have, let us say, twice of xi 1 into omega n1 is equal to alpha plus beta into omega n1 square. For mode 2, we will have twice of xi 2 into omega n2 is equal to alpha plus beta into omega n2. So xi 1 is the modal damping factor of first mode, omega 1 is the natural frequency of first mode, xi 2 is the modal damping factor of second mode, and omega n2 is the natural frequency of second mode. So now you have these two equations. Now if you look at these two equations, so these two equations can be solved for alpha and beta. So if you solve for alpha and beta, then you have your damping matrix. But to solve for alpha and beta, omega n1 and omega n2, you can either take from the experimental characterization, or you can also take this from the modal analysis through this finite element. But for zeta 1 and xi 1 and xi 2, you have to depend on the experiments. These xi 1 and xi 2 are not the natural coordinates, but they are damping factors. So xi 1 is the damping factor in mode 1 and xi 2 is the damping factor in mode 2. So how do you get this? So one is you can use the logarithmic decrement. So from the free vibration, so you have the physically the structure is existing, you can conduct experiment and get xi 1 and xi 2. or you can use, so for that either you can use a half power point method or you can use logarithmic decrement. So these are the various ways you can get xi1 and xi2. So suppose you want to use the logarithmic decrement. So in that case, let us say if you have a structure and now you excite it, and let's say you take the displacement at one point w, let us say, and this axis you have time t, and give the initial disturbance such a way that the structure vibrates, let's say in first mode. So then you record the response, and let us say the response is like this. And so here let us say the amplitude is w1, and here the, let's say next cycle, here the amplitude is w2, and this the time interval, this time interval is 2 pi by omega n1. So experimentally also you can get your omega n1 if you know this time period, and you get w1 and w2. So from this you find out what is known as logarithmic decrement. So logarithmic decrement. So now the first mode you will have delta 1 is known as the logarithmic decrement, that is natural logarithm of w1 upon w2, and this can be written as 2 pi xi1 upon 1 minus xi1 square root. So from this you solve for xi1. Similarly, you excite the structure in another mode and then record the this free vibration response, and then you get the delta 2 logarithmic decrement, that would be again equal to, say, let me say another mode is, let me also put the mode. So here I will say superscript 1 here I will say superscript 2 so w22, and this would be equal to 2 pi into xi2 upon 1 minus xi2 square. So from this you can solve for xi2. So once you have xi1 and xi2, so come to these two equations. These two equations solve for alpha and beta, and once you have your alpha and beta, then your damping matrix is ready. Now that you can use in the subsequent dynamic response analysis. Either you want to do harmonic analysis, that is steady state frequency response for a linear system, or you want to do transient analysis, free transient response analysis, or force response analysis. So you can do all of those, including this damping matrix C, which is alpha m plus beta k. So that is how you incorporate basically damping in your finite element model if your constitutive relation is a basically the elastic constitutive relation. So you don't have any dissipation in that. So I think this is where I want to stop. And if you have any questions and doubts, you can ask. Yeah, so anybody, any question, any doubt?
Hello, sir.
Yeah.
Am I audible?
Yeah, you are audible. Please go ahead.
So you have said that these alpha and beta are calculated experimentally. So
yeah, they are based on the experimental data.
Yes, sir. So like if I'm simulating for any force response where the loading is very different, complex loading, like it is changing with time. So will that affect how we are modeling the damping? Like is there any other factors?
Now if you look at the damping here, so we are just determining the damping based on two modes, as you see, the damping factor in just two modes. So if the force is a function of time and it is exciting different modes, and if the modes which are excited are different from the modes which are used to find out this damping matrix, then know that alpha and beta are xi1 and xi2, then the damping will not be that accurate, but still usually what is the observation that in the experimental systems, the damping factor for different modes increases with the frequency. And now if you look at this equation, what I have written, so if you after you have solved for alpha and beta using the damping factor of just two modes, then you can write the expression for xi I will be 1/2 into omega ni plus beta times omega ni. So this is what the xi I. Now for the damping factor for any other mode is this term, of course, will contribution of this term would decrease with increasing frequency, but this would increase. So you would see that this model also represents increasing damping factor with the increasing frequency or the mode number. So more or less the damping would be accounted for correctly for different modes, even if the higher modes are excited due to dynamic force. So even though we are just using two modes to find out alpha and beta, but the increasing damping with frequency or the modes is actually captured by this Rayleigh proportional damping model. So it would still be accurately represented for other modes. Now, if, maybe the specific situation you want to be very accurate, and you know that the two modes which would participate in the dynamic response, they are important. And for those modes, if you know the damping factor, then you can get the alpha and beta from that, so that for those two modes you will have the accurate damping, and other modes would be approximated. So you can, like that, you can model it. Yeah, so your answer to your question is approximately the damping is accurately represented for other modes also, other than the modes for which which are used for finding out alpha and beta.
Okay, sir. Okay.
Yeah.
Sir, but for all cases, like, is it possible to model damping just with Rayleigh model?
No, it is now not for all modes. You cannot exact damping factors of all the modes cannot be incorporated just in this 2-parameter model.
No, sir. I'm telling, sir, like, for different cases, because, sir, I was reading one book on vibration, and there they mentioned something about a structural damping.
Yeah.
So like, is that also something like Rayleigh model, like a different version of Rayleigh model?
Yeah, you get that structural damping. You can model using this Rayleigh damping proportional model. You can model that using this Rayleigh proportional damping model. You can capture the structural damping. Yeah.
So, sir, will you be discussing that one also with us, or like, will we be like only doing Rayleigh damping in this class?
No, I'm going to do only Rayleigh damping.
Okay, sir.
Yeah.
Okay, sir.
Are there any other questions? Anybody? Any other question? So if there are no questions, I am stopping here. Thank you all for your attention.